The universe has rules, at least that's what we thought. For nearly a century, cosmologists have operated under a single unshakable assumption: nothing can be older than the Big Bang. The Big Bang marks time zero, the moment when space, time, matter and energy exploded into existence roughly 13.8 billion years ago. Everything we see, from the smallest particle to the largest galaxy cluster, emerged after that singular event. It's the foundation of modern cosmology, the starting point from which all cosmic history flows. But what happens when a telescope peers deeper into space than ever before and finds something that shouldn't exist? What happens when astronomers discover a galaxy so ancient, so fully formed, that it appears to predate the very event that supposedly created it? This isn't science fiction. This is the reality James Webb's Space Telescope has thrust upon us. In early observations, Webb detected a galaxy designated JADES GSZ 130, whose light has travelled more than 13.5 billion years to reach us. That places its formation less than 300 million years after the Big Bang. But here's the problem. This galaxy isn't a cloud of chaotic gas or a scattering of primitive stars. It's massive, structured and filled with stars that, by all accounts, should have taken billions of years to form. The numbers don't add up, the timeline doesn't work, and the implications are staggering. For decades, cosmologists built models predicting what the early universe should look like. Galaxies were supposed to start small and grow slowly through mergers and gradual star formation. The first galaxies should have been dim, irregular, and lacking in heavy elements. Yet Webb is finding the opposite: bright, massive, well-organized galaxies appearing far earlier than any model predicted. Some of these galaxies are so mature that, if current theories hold, they would need to have started forming before the Big Bang itself, a logical impossibility that threatens to unravel everything we thought we understood about cosmic history. This discovery isn't just surprising, it's destabilizing. It forces scientists to confront uncomfortable questions about the Big Bang timeline, the nature of galaxy formation, and whether our fundamental understanding of the universe's first moments might be incomplete or worse, fundamentally wrong. The James Webb Space Telescope didn't just find an old galaxy, it found a crack in the foundation of cosmology itself, the cosmic dark ages and the first light. The universe didn't begin with light. For hundreds of thousands of years after the Big Bang, the cosmos was a seething plasma so hot and dense that photons couldn't travel freely. Protons and electrons collided constantly, scattering light in every direction, rendering the universe opaque. This epoch, known as the photon epoch, was a luminous fog where nothing could be seen because light itself was trapped. Around 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. This event, called recombination, allowed photons to finally travel unimpeded through space. The universe became transparent, and the cosmic microwave background radiation we detect today was released a faint afterglow still observable in every direction. But transparency didn't mean illumination. Once recombination occurred, the universe plunged into darkness. This period is called the Cosmic Dark Ages, and it lasted for roughly 100 to 200 million years. During this time, the universe was filled with neutral hydrogen gas, but no stars had yet ignited. No galaxies had yet formed. Space was cold, dark, and silent, an endless void punctuated only by the faint hum of residual radiation cooling into the microwave spectrum. Gravity, however, was already at work. Tiny density fluctuations imprinted during the Big Bang began to pull hydrogen gas into clumps. These clumps grew denser, collapsing under their own weight, until eventually the first stars ignited. These primordial stars, known as population 3 stars, were nothing like the Sunday. They were massive, perhaps 100 to 300 times the Sun's mass, and composed almost entirely of hydrogen and helium. No heavier elements existed yet, because no stars had lived and died to create them. Population 3 stars burned ferociously, living only a few million years before exploding as supernovae. Their deaths seeded the cosmos with the first carbon, oxygen, iron, and other heavy elements, setting the stage for the next generation of stars and the formation of the first galaxies. The transition from the Dark Ages to the epoch of reionization marks one of the most significant transformations in cosmic history. As the first stars blazed to life, their ultraviolet radiation began ionizing the surrounding hydrogen gas, stripping electrons from atoms and turning vast regions of space back into plasma. This process didn't happen all at once. It spread outward in bubbles around the earliest stars and galaxies, gradually merging until the entire universe became reionized, roughly 1 billion years after the Big Bang. For decades, astronomers have tried to observe this critical transition directly. Ground-based telescopes can't see it. The light from that era has been stretched by the universe's expansion into the infrared spectrum, which Earth's atmosphere absorbs. Even the Hubble Space Telescope, despite its remarkable sensitivity, could only glimpse the tail end of reionization. It detected a few galaxies from around 400 to 500 million years after the Big Bang, but it couldn't see the true beginning, the moment when the first stars and galaxies flickered to life in the primordial darkness. James Webb was specifically designed to pierce this veil. Its massive mirror and advanced infrared instruments allow it to detect the faintest, most redshifted light from the universe's infancy. Within months of beginning operations, Webb shattered expectations. It found galaxies at redshifts of 12, 13, even 14, corresponding to times as early as 200 to 300 million years after the Big Bang. These weren't faint, irregular smudges. They were structured, luminous, and far more massive than any model had predicted. The existence of such galaxies so early poses a fundamental problem. Galaxy formation isn't instantaneous. It requires time for dark matter halos to collapse, for gas to cool and condense, for stars to form and enrich the interstellar medium with heavy elements. The standard model of cosmology, known as Lambda CDM, predicts that this process should take at least 500 million to 1 billion years. Yet Webb is detecting galaxies that appear fully formed in half that time or less. One of the most perplexing examples is JADESGSZ 130, a galaxy observed at a redshift of 13.2. Its light has travelled 13.5 billion years, meaning we're seeing it as it existed just 325 million years after the Big Bang. Spectroscopic analysis reveals that this galaxy contains stars that have already undergone multiple generations of formation and death. It shows signatures of heavy elements like carbon and oxygen, which can only be produced in stellar cores and dispersed by supernovae. Yet for those processes to have occurred, the galaxy's first stars must have formed much earlier, perhaps only 100 to 150 million years after the Big Bang. That timeline leaves almost no room for the cosmic dark ages. If galaxies like JADESGSZ 130 were already mature by 325 million years, then the first stars must have ignited almost immediately after recombination. But that contradicts everything we know about how structure forms in the universe. Dark matter halos need time to grow, gas needs time to cool, stars need time to fuse elements and explode. Compressing all of that into less than 200 million years requires either radically different physics in the early universe or a fundamental misunderstanding of the Big Bang timeline itself. Webb's discoveries have forced cosmologists to confront an uncomfortable possibility. The models that have guided our understanding of the universe for decades may be incomplete. The cosmic dark ages might not have been as dark or as long as we thought. And if galaxies formed faster than predicted, it suggests that the processes governing the early universe were far more efficient or far stranger than current theories allow. Redshift and the measurement of cosmic time. Understanding how astronomers determine the age of distant galaxies requires grasping one of the most fundamental concepts in cosmology: redshift. When light travels through expanding space, its wavelength stretches. A photon emitted as blue light from a distant galaxy arrives at Earth shifted toward the red end of the spectrum. The farther the galaxy, the more space has expanded during the light's journey, and the greater the redshift. This simple relationship allows astronomers to measure cosmic distances, and by extension, cosmic time. Redshift is quantified using the letter Z. A galaxy with Z equals 1 is seen as it was roughly 7.7 billion years ago. A galaxy at Z equals 6 corresponds to about 12.7 billion years ago, less than 1 billion years after the Big Bang. The Hubble Space Telescope struggled to detect galaxies beyond Z equals 8, which corresponds to around 13.2 billion years ago, roughly 600 million years after the universe began. Beyond that, The light becomes so faint and so stretched into the infrared that Hubble's instruments simply couldn't see it. James Webb was built to shatter this barrier. Its infrared sensitivity extends far beyond Hubble's range, allowing it to detect galaxies at redshifts of 10, 12, 14, and possibly higher. Each increment in redshift corresponds to peering deeper into the past, closer to the moment of the Big Bang itself. A galaxy at z equals 13, for example, is observed as it existed just 300 to 350 million years after the universe began, a time when, according to standard models, galaxies should barely exist at all. The process of measuring redshift begins with spectroscopy. When light from a galaxy passes through a prism or diffraction grating, it splits into a spectrum, a rainbow of wavelengths revealing which elements are present in the galaxy's stars and gas. Each element produces a unique pattern of spectral lines. Hydrogen emits light at specific wavelengths, as do oxygen, carbon, and other elements. In a nearby galaxy, these lines appear at their expected wavelengths, but in a distant galaxy, the lines are shifted toward longer, redder wavelengths by the expansion of space. By measuring how much the spectral lines have shifted, astronomers can calculate the redshift and, from that, determine the galaxy's distance and age. For the most distant galaxies, this shift is so extreme that ultraviolet spectral lines are stretched all the way into the infrared. That's why James Webb's near-infrared and mid-infrared instruments are so crucial. They're specifically designed to capture light that began its journey as visible or ultraviolet radiation, but has been redshifted into wavelengths invisible to human eyes. One of Webb's early spectroscopic confirmations involved a galaxy initially catalogued as JADES-GSZ130. Preliminary photometric data measurements based on brightness in different filters suggested a redshift around 13, but photometry alone can be misleading. Certain types of dusty, nearby galaxies can mimic the colours of extremely distant ones, leading to false identifications. To confirm the redshift, astronomers needed spectroscopy. Webb's near-spec instrument obtained a detailed spectrum, revealing spectral lines shifted so far into the infrared that they confirmed a redshift of 13. 2. Placing the galaxy just 325 million years after the Big Bang. The confirmation sent shockwaves through the astronomical community. Not only was the galaxy's existence surprising, but its properties were even more shocking. Spectroscopic analysis revealed that JADES-GSZ130 contains stars with metallicities, abundances of elements heavier than hydrogen and helium, far higher than expected for such an early galaxy. In the standard model of galaxy formation, the first stars are metal-free, composed only of primordial hydrogen and helium. When these stars explode as supernovae, they enrich the surrounding gas with heavier elements, which are incorporated into the next generation of stars. This process takes time, hundreds of millions of years, at minimum, yet here was a galaxy, observed less than 350 million years after the Big Bang, already showing signs of metal enrichment. That implies multiple generations of stars had already lived and died. But if the first stars formed around 150 million years after the Big Bang, and each generation takes tens to hundreds of millions of years to evolve, the timeline becomes impossibly tight. The numbers simply don't fit within the current cosmological framework. Adding to the puzzle is the galaxy's mass. Stellar mass estimates derived from its luminosity suggest JADES-GSZ130 contains roughly 1 billion solar masses worth of stars. For comparison, the Milky Way contains about 60 billion solar masses in its stellar disk, so this early galaxy is already a significant fraction of a mature spiral's stellar content. But building 1 billion solar masses of stars in less than 300 million years requires an extraordinary rate of star formation, far higher than what's observed in most galaxies today, and far higher than what early universe models predict. Standard models suggest that in the first few 100 million years after the Big Bang, star formation should be inefficient, gases diffuse, dark matter halos are still collapsing, and the conditions for sustained star formation haven't yet stabilized. Galaxies should grow slowly, accreting gas over time and gradually building stellar mass through merger events and prolonged star formation episodes. Yet Webb is finding galaxies that appear to have bypassed this gradual process entirely, forming stars at prodigious rates almost immediately after the cosmic dark ages ended. The redshift measurements Webb provides are forcing astronomers to reconsider fundamental assumptions about the early universe. If galaxies at z equals 13 are already mature, then the processes that drive galaxy formation must operate far more rapidly than current models allow. Either the efficiency of star formation was dramatically higher in the early universe, or some unknown mechanism accelerated the collapse of dark matter halos and the cooling of gas, enabling galaxies to form in a fraction of the expected time. The Lambda CDM model and its predictions. For nearly a century, cosmologists have relied on the Lambda CDM model to explain the universe's structure and evolution. This framework, which stands for Lambda Cold Dark Matter, has become the standard model of cosmology, a set of equations and assumptions that describe how the universe expanded from the Big Bang, how matter clumped together under gravity, and how galaxies, stars, and planets eventually formed. It has been tested against countless observations, from the cosmic microwave background radiation to the large-scale distribution of galaxies, and it has passed every test until now. The Lambda CDM model rests on a few key components. Lambda refers to the cosmological constant, a term Albert Einstein introduced to represent dark energy, the mysterious force driving the universe's accelerating expansion. Cold dark matter, or CDM, refers to the invisible matter that doesn't emit light but exerts gravitational pull, shaping the distribution of galaxies across the cosmos. Together, these components account for about 95% of the universe's total energy density. Ordinary matter, protons, neutrons, electrons, everything we can see makes up less than 5%. According to Lambda CDM, the universe began 13.8 billion years ago in a hot, dense state and has been expanding ever since. In the first moments after the Big Bang, tiny quantum fluctuations in density were stretched to cosmic scales by inflation, a brief period of exponential expansion. These fluctuations became the seeds of all structure in the universe. Regions that were slightly denser than average attracted more matter through gravity, growing into dark matter halos. Over time, ordinary matter, mostly hydrogen and helium gas, fell into these halos, cooled and condensed to form the first stars and galaxies. The model makes specific predictions about when and how galaxies should form. In the early universe, dark matter halos were small and grew through a hierarchical process. Smaller halos merged to form larger ones, and galaxies within those halos grew by accreting gas and merging with other galaxies. This process is slow and inefficient at first. The first galaxies, forming a few 100 million years after the Big Bang, should be small, dim, and irregular. Over billions of years, they merge and grow into the massive spiral and elliptical galaxies we see today. Lambda CDM also predicts the timeline of reionization, the period when the first stars and galaxies ionize the neutral hydrogen gas filling the universe. According to the model, reionization should have begun around 400 to 500 million years after the Big Bang, and completed by about 1 billion years. Before James Webb, observations from Hubble and other telescopes were broadly consistent with this timeline. Hubble detected galaxies at redshifts around 8 to 10, corresponding to 500 to 600 million years after the Big Bang, and their properties matched expectations. They were small, faint, and relatively metal-poor. But Webb's observations have upended these predictions. Within its first year of operation, Webb discovered dozens of galaxies at redshifts of 11, 12, 13, and even higher, far earlier than Lambda CDM models anticipated. More troubling still, these galaxies aren't small and dim. Many are bright, massive, and show signs of advanced stellar populations. Some contain 1 billion solar masses of stars or more, implying that star formation began much earlier and proceeded much faster than the model allows. Consider JADESGSZ 130 again. At a redshift of 13.2, this galaxy is observed just 325 million years after the Big Bang. Lambda CDM predicts that at this time, galaxies should be in their infancy, small clumps of stars embedded in dark matter halos, with star formation rates of perhaps a few solar masses per year. Yet JADESGSZ 130 contains roughly 1 billion solar masses of stars, suggesting an average star formation rate of several hundred solar masses per year, sustained over tens to hundreds of millions of years. That's an order of magnitude higher than the model predicts. The problem compounds when you consider stellar evolution. The stars in JADES, GSZ 130 aren't all young. Spectroscopic analysis reveals the presence of heavy elements like carbon, oxygen, and possibly even iron. These elements can only be created inside stars through nuclear fusion and dispersed into space when those stars explode as supernovae. The presence of these elements means that at least one generation of stars had already formed, lived, and died by the time we observed this galaxy. But each generation of stars takes tens to hundreds of millions of years to evolve depending on their mass. Cramming multiple generations into the first 325 million years of the universe leaves almost no time for the initial formation of dark matter halos and the collapse of gas into the first stars. Cosmologists have proposed several ways to reconcile Webb's observations with Lambda CDM. One possibility is that star formation in the early universe was far more efficient than we thought. Perhaps the cooling of gas, the collapse of dark matter halos, and the ignition of stars happened faster in the dense environment of the early universe. Higher densities could lead to more rapid gravitational collapse, and the lack of heavy elements, which normally help gas cool and form stars, might paradoxically have led to the formation of extremely massive stars that burned brightly but briefly, accelerating the enrichment process. Another possibility involves the nature of dark matter itself. Lambda CDM assumes that dark matter is cold, meaning its particles move slowly and clump together efficiently under gravity. But some physicists have suggested that if dark matter were slightly warmer, if its particles move faster, it could change the timeline of structure formation. Warm dark matter would smooth out small-scale density fluctuations, delaying the formation of the smallest halos but potentially accelerating the collapse of larger ones. This could, in theory, lead to the rapid formation of massive galaxies in the early universe. JADES/GSZ 130 and the crisis of early galaxies. Among the thousands of galaxies James Webb has observed, one stands out as particularly problematic for cosmology: JADES/GSZ 130. This galaxy, detected in the JWST Advanced Deep Extragalactic Survey, exists at a redshift of 13.2, placing it just 325 million years after the Big Bang. At first glance, finding a galaxy at such an early time might seem remarkable but not necessarily paradigm-shattering. After all, Webb was designed to detect the universe's first galaxies. The real crisis emerges when you examine what kind of galaxy JADES/GSZ 130 actually is. Spectroscopic observations reveal that this galaxy is not a faint proto-galaxy struggling to ignite its first stars. It's a luminous, massive system containing roughly 1 billion solar masses of stars. For context, the Milky Way's stellar disk contains about 60 billion solar masses, so this early galaxy already holds a significant fraction of a mature galaxy's stellar content, despite existing when the universe was only 2% of its current age. The sheer amount of stellar mass packed into such a young galaxy defies standard models of galaxy formation. The problem deepens when you consider stellar lifetimes. Massive stars, those with masses greater than 8 solar masses, live only a few million to a few tens of millions of years before exploding as supernovae. Lower mass stars like the Sun can live for billions of years. If JADES/GSZ 130 formed its stars in a single burst, the most massive stars would have already died by the time we observe the galaxy. But spectroscopic analysis shows a mix of stellar populations, including signs of ongoing star formation alongside older stars. This suggests that star formation in JADES/GS 130 was not a single event, but a sustained process lasting tens to hundreds of millions of years. Even more troubling is the presence of heavy elements. Spectroscopy reveals absorption and emission lines corresponding to carbon, oxygen, and possibly nitrogen elements that can only be produced inside stars through nuclear fusion. In the first moments after the Big Bang, the universe contained only hydrogen, helium, and trace amounts of lithium. Every other element on the periodic table had to be forged in stellar cores and released into space when those stars died. The presence of these elements in JADES/GSZ 130 means that at least one generation of stars had already formed, lived, fused elements in their cores, and exploded as supernovae before the galaxy reached the state we observe. This creates a timeline crisis. Let's work backward from the observation at 325 million years after the Big Bang. The presence of heavy elements means the first stars must have formed, evolved, and died before this time. Massive stars can complete their life cycles in as little as 3 to 5 million years, so in theory, the first generation of stars could have enriched the interstellar medium relatively quickly. But those first stars had to form from pristine gas with no heavy elements, which means they were likely very massive, short-lived population 3 stars. These stars would have produced some heavy elements, but not in the quantities observed in JADES/GSZ 130. To match the observed metallicity, at least 2 or 3 generations of stars would need to have formed, lived, and died. Each generation takes tens to hundreds of millions of years to complete its cycle, depending on the stellar masses involved. If we assume an average of 50 to 100 million years per generation, then 3 generations would require 150 to 300 million years. That brings us back to the cosmic dark ages, suggesting that the first stars must have ignited almost immediately after recombination, perhaps as early as 50 to 100 million years after the Big Bang. But Lambda CDM models predict that structure formation should be slow at first. Dark matter halos take time to collapse and grow through mergers. Gas takes time to cool and condense. The first stars shouldn't ignite until at least 100 to 200 million years after the Big Bang, and early star formation should be inefficient, producing only small numbers of stars in isolated halos. The idea that galaxies like JADES/GSZ 130 could have assembled entire stellar populations, complete with multiple generations of chemical enrichment in less than 300 million years, is incompatible with these predictions. One proposed explanation is that star formation in the early universe was far more efficient than current models assume. Perhaps the dense, metal-free gas of the primordial universe collapsed more readily under gravity, forming stars at rates hundreds of times higher than what we see today. Some simulations suggest that the first galaxies might have experienced brief but intense starbursts, converting enormous amounts of gas into stars in just a few million years. If true, this could explain how JADES/GSZ 130 built its stellar mass so quickly. Another possibility is that the galaxy formed through rapid mergers of smaller proto-galaxies. In this scenario, dozens or even hundreds of small halos, each containing a few million solar masses of stars, collided and merged in quick succession. Building JADES/GSZ 130 through hierarchical assembly, mergers can trigger bursts of star formation by compressing gas, potentially accelerating the process. However, this explanation requires an unusually high rate of mergers in the early universe, and it's unclear whether enough small halos could have formed and merged in the available time. A more radical possibility is that our understanding of the Big Bang timeline is wrong. If the universe is older than 13.8 billion years, or if the early expansion rate was different than we calculate, then galaxies like JADES/GSZ 130 would have had more time to form. The Hubble tension, the discrepancy between different measurements of the universe's expansion rate, hints at this possibility. If the true expansion rate is higher than the CMB-derived value, it implies the universe expanded faster in the past, meaning it reached its current size in less time, making it younger, not older. But if the expansion rate was lower in the very early universe, before dark energy began dominating, then more time would have been available for structure formation. The problem of stellar metallicity in ancient galaxies. One of the most confounding aspects of James Webb's high redshift galaxy discoveries isn't just their unexpected mass or brightness, it's their chemistry. When astronomers analyze the spectra of galaxies like JADES/GSZ 130, they're looking for specific wavelengths of light absorbed or emitted by different elements. These spectral lines act like chemical fingerprints, revealing which elements are present in the galaxy's stars and gas. What Webb has found is deeply troubling for standard cosmological models. These ancient galaxies contain substantial amounts of heavy elements far sooner than they should. The standard model of stellar nucleosynthesis describes how stars create heavy elements. During a star's main sequence lifetime, hydrogen fuses into helium in its core. As the star ages, helium fuses into carbon and oxygen. In more massive stars, fusion continues, creating neon, magnesium, silicon, and eventually iron. When massive stars explode as supernovae, the intense heat and pressure of the explosion forge even heavier elements like gold, platinum, and uranium. These elements are ejected into space at tremendous speeds, mixing with the surrounding interstellar medium. The next generation of stars that forms from this enriched gas will contain higher metallicities than the generation before. This process is inherently sequential and time-consuming. The first generation of stars, population 3 stars, must form from pristine gas, live their lives, and die before the second generation can incorporate their chemical products. Population 3 stars are thought to have been extremely massive, perhaps 100 to 300 solar masses, living only a few million years before exploding. Their supernovae would have enriched their immediate surroundings with the first heavy elements, allowing slightly less massive, longer-lived stars to form in the next generation. Over hundreds of millions of years, successive generations of stars would gradually increase the metallicity of the galaxy. Lambda CDM models predict that at 300 to 400 million years after the Big Bang, galaxies should have very low metallicities, perhaps only 1 to 10% of the Sun's metallicity, which serves as a reference point. The Sun, which formed about 4.6 billion years ago, has a metallicity enriched by billions of years of prior stellar evolution in the Milky Way. Early galaxies, by contrast, should show the chemical signatures of only 1 or 2 generations of stars, mostly hydrogen and helium, with just a sprinkle of carbon and oxygen. Yet when astronomers obtained spectra of JADES-GSZ130, they detected strong emission lines from carbon and oxygen, along with possible signatures of nitrogen and even heavier elements. The measured metallicity is far higher than models predict, perhaps 20 to 50% of solar metallicity, or even more in localized regions. This implies that not 1 or 2, but multiple generations of stars had already cycled through their lifespans, each contributing to the chemical enrichment of the galaxy. To reach such high metallicities so early requires either an extraordinarily rapid succession of stellar generations or a star formation process fundamentally different from what we observe in the universe today. One possibility is that population 3 stars were far more common and short-lived than previously thought. If the first stars formed in huge numbers and exploded within a few million years, they could have rapidly seeded the early universe with heavy elements. Some models suggest that the first galaxies might have experienced top-heavy initial mass functions, meaning they produced disproportionately more massive stars than modern galaxies do. Massive stars burn through their fuel quickly and die young, so a galaxy dominated by massive stars would undergo rapid chemical enrichment. However, this scenario has its own problems. Massive stars are extremely luminous, and if early galaxies were dominated by them, they should appear much brighter than observed. Webb detects luminous galaxies, but not to the extent expected if they were filled almost entirely with supermassive stars. Another explanation involves extremely efficient mixing of the interstellar medium. When a supernova explodes, it doesn't enrich the entire galaxy uniformly. The heavy elements are concentrated in expanding shells of gas around the explosion site. For the galaxy as a whole to become metal-rich, these ejecta need to mix thoroughly with the surrounding gas. In modern galaxies, this mixing is driven by turbulence, stellar winds, and subsequent generations of supernovae. But mixing takes time, tens to hundreds of millions of years. If mixing in early galaxies happened faster, perhaps due to higher gas densities or more vigorous turbulence, it could explain the observed metallicities. Some astrophysicists have proposed that the first galaxies might have experienced supernova-driven outflows that expelled metal-enriched gas into the surrounding dark matter halo, then allowed it to fall back and mix with fresh gas. This cycle of ejection and accretion could accelerate chemical enrichment by continuously recycling enriched material. However, simulations of this process in early galaxies are still uncertain, and it's unclear whether outflows alone can explain the high metallicities Webb observes. The metallicity problem is compounded by observations of other high redshift galaxies. JADES-GSZ130 is not an isolated anomaly. Webb has detected numerous galaxies at redshifts between 10 and 14, and many show similarly high metallicities. In some cases, emission lines indicate metal abundances comparable to galaxies billions of years older. This pattern suggests a systematic issue with our understanding of early star formation and chemical enrichment, not just a quirk of one unusual galaxy. Metallicity measurements also carry implications for planet formation. Heavy elements are the building blocks of rocky planets. If galaxies were already metal-rich within the first few 100 million years of the universe, it means the raw materials for planet formation were available far earlier than previously thought. Some researchers have speculated that planets, and possibly even life, could have emerged in the universe much sooner than standard models predict, though detecting such ancient planetary systems remains far beyond current observational capabilities. The Hubble tension and the age of the universe. For decades, astronomers have relied on the Hubble constant, the rate at which the universe is expanding, to calculate the age of the cosmos. This single number, typically expressed in units of kilometers per second per megaparsec, determines how fast galaxies are receding from one another and, by extension, how long ago the Big Bang occurred. But in recent years, a troubling discrepancy has emerged. Different methods of measuring the Hubble constant yield different values. This mismatch, known as the Hubble tension, has become one of the most pressing problems in cosmology, and it may hold the key to understanding why James Webb is finding galaxies that shouldn't exist. The most precise measurement of the Hubble constant comes from observations of the cosmic microwave background, or CMB. Satellites like Planck have mapped the tiny temperature fluctuations in this relic radiation with extraordinary accuracy. By fitting these fluctuations to the Lambda CDM model, cosmologists derive a Hubble constant of approximately 67 km per second per megaparsec. This value implies that the universe is about 13.8 billion years old and has been expanding at a specific, predictable rate since the Big Bang. But when astronomers measure the Hubble constant using local observations, specifically by studying Cepheid variable stars and type Ia supernovae in nearby galaxies, they get a different answer: roughly 73 km per second per megaparsec. This 9% discrepancy might seem small, but in cosmology, it's enormous. The two measurements should agree if our understanding of cosmic expansion is correct. The fact that they don't suggest that something fundamental is missing from the Lambda CDM model. The implications of this tension extend directly to the problem of early galaxies. If the true Hubble constant is closer to 73, it means the universe is expanding faster than the CMB measurement suggests. A faster expansion rate implies the universe reached its current size in less time, making it younger than 13.8 billion years. Some estimates based on the higher Hubble constant place the universe's age closer to 12.5 or 13 billion years. While this might seem like a minor adjustment, it has profound consequences for galaxy formation timelines. A younger universe gives even less time for galaxies like JADES GSZ130 to form, making their existence even more problematic. Conversely, if the CMB-derived Hubble constant of 67 is correct, then the local measurement must be wrong or influenced by some unknown systematic error. But multiple independent teams using different methods have confirmed the higher value. The most prominent of these is the SH0ES, supernova H0, for the Equation of State project, led by astronomer Adam Riess, which has refined the local Hubble constant measurement to unprecedented precision. Their result consistently hovers around 73, with uncertainties small enough that random error cannot explain the discrepancy. One possible explanation for the Hubble tension is that the universe's expansion rate has not been constant over time. Lambda CDM assumes that the cosmological constant dark energy is truly constant, exerting the same repulsive force throughout cosmic history. But if dark energy has evolved over time, growing stronger or weaker, it could alter the universe's expansion history in ways not captured by current models. Some physicists have proposed models of quintessence, where dark energy is not a constant, but a dynamic field that changes over billions of years. If dark energy was weaker in the early universe, the expansion rate would have been different then than it is now, potentially affecting the timeline of galaxy formation. Another possibility involves the nature of dark matter itself. Lambda CDM assumes that dark matter is cold, meaning its particles move slowly and clump together efficiently under gravity. But if dark matter interacts with itself or with ordinary matter in ways we haven't accounted for, it could alter the formation of structure in the early universe. Some researchers have explored models where dark matter has slight self-interactions, allowing it to redistribute itself within halos and potentially accelerating the collapse of gas into galaxies. While these models remain speculative, they represent one avenue for reconciling the rapid appearance of massive galaxies with the constraints of the Hubble tension. A more radical interpretation is that the Hubble tension signals a breakdown of the Lambda CDM model itself. If the universe's expansion history is more complicated than Lambda CDM allows, it could mean that our entire framework for understanding cosmology needs revision. Some physicists have proposed models involving extra dimensions, modified gravity theories, or cyclic cosmologies where the universe undergoes repeated cycles of expansion and contraction. In these scenarios, the age of the universe might not be as straightforward as the time since the Big Bang structure could have existed before the most recent expansion phase, potentially explaining why galaxies appear so mature so early. James Webb's observations add another layer of complexity to the Hubble tension. If galaxies at redshifts of 12 or 13 are already massive and metal-rich, they must have begun forming stars much earlier than Lambda CDM predicts. But if the universe is younger than 13.8 billion years, as the higher Hubble constant suggests, then the timeline becomes even tighter. This creates a catch. 2. A younger universe gives less time for galaxy formation, but the existence of early galaxies demands more time. The only way to resolve this paradox is to either find a way to dramatically accelerate galaxy formation, or to revise our understanding of the universe's age and expansion history. Some astronomers have suggested that the resolution might lie in the properties of the first stars and galaxies themselves. If the initial mass function, the distribution of stellar masses, was heavily skewed toward massive stars in the early universe, star formation could have proceeded much faster. Massive stars produce heavy elements and explode as supernovae within a few million years, rapidly enriching their surroundings and enabling subsequent generations of stars to form more quickly. This top-heavy initial mass function could compress what normally takes hundreds of millions of years into a much shorter timescale. Supermassive black holes in the infant universe. Among the many surprises James Webb has unveiled, perhaps none is more perplexing than the discovery of supermassive black holes in galaxies existing less than 1 billion years after the Big Bang. These black holes, with masses ranging from millions to over 1 billion times that of the Sun, pose a profound challenge to astrophysics. The problem is simple. Supermassive black holes take time to grow, and the universe at redshifts of 10 or higher simply hasn't existed long enough for them to have formed through conventional processes. The limiting factor is the Eddington limit, named after British astrophysicist Arthur Eddington. When a black hole accretes matter, the infalling material heats up and emits intense radiation. This radiation exerts an outward pressure on the surrounding gas, counteracting the inward pull of gravity. If the black hole tries to accrete too much matter too quickly, the radiation pressure becomes so strong that it blows away the infalling gas, effectively capping the black hole's growth rate. Under typical conditions, a black hole can roughly double its mass every 50 million years. Starting from a 1-0 solar mass stellar black hole, it would take hundreds of millions to a few billion years to reach 1 million solar masses and much longer to reach 1 billion. Yet James Webb has detected galaxies at redshifts of 10 to 12, corresponding to 400 to 600 million years after the Big Bang, that harbour black holes with masses exceeding 100 million solar masses. Some candidates at even higher redshifts may contain billion solar mass black holes. If these black holes began as stellar remnants around 100 to 200 million years after the Big Bang, they would have had only 200 to 500 million years to grow. Even if they accreted matter continuously at the Eddington limit, the maximum sustainable rate, they couldn't have reached the observed masses. Something about the standard picture of black hole growth must be wrong. One possibility is that the first black holes didn't form from stars at all. Instead, they might have formed directly from the collapse of massive clouds of primordial gas. In the early universe, before the first stars ignited, regions of exceptionally high gas density could have collapsed under their own gravity, forming black holes with initial masses of thousands or even tens of thousands of solar masses. These direct collapse black holes would skip the stellar phase entirely, giving them a head start on growth. If such seeds existed, they could have reached supermassive scales much faster than stellar remnant black holes. Direct collapse black hole formation requires specific conditions. The gas must be dense enough to collapse but not fragment into individual stars. This typically happens in regions where molecular hydrogen, the molecule that normally cools gas and allows it to fragment, is scarce or destroyed. Intense ultraviolet radiation from nearby galaxies can dissociate molecular hydrogen, creating pockets of hot, atomic hydrogen that collapses into massive black holes rather than stars. Some simulations suggest that direct collapse black holes could have formed in the first few 100 million years after the Big Bang, seeding the supermassive black holes we observe in early galaxies. A third possibility is that black holes in the early universe accreted matter far faster than the Eddington limit allows. Some astrophysicists have proposed super-Eddington accretion, where black holes grow through rapid, chaotic inflow of gas that somehow evades the usual radiation pressure limits. This could occur if the infalling gas is clumpy rather than smooth, allowing pockets of matter to fall in without being blown away. Alternatively, if black holes were surrounded by thick envelopes of gas and dust that absorbed outgoing radiation, the effective radiation pressure on infalling material could be reduced, permitting faster growth. Observations of high redshift quasars, extremely luminous galaxies powered by supermassive black holes, provide some support for super-Eddington accretion. Quasars at redshifts of 6 to 7, corresponding to less than a billion years after the Big Bang, are among the brightest objects in the universe. Their luminosity implies that their central black holes are consuming matter at prodigious rates, possibly exceeding the Eddington limit. If such rapid accretion was common in the early universe, it could explain how supermassive black holes grew so quickly. The role of black hole mergers also cannot be ignored. In the early universe, galaxies were closer together and collided more frequently. When two galaxies merge, their central black holes eventually spiral toward each other and merge, creating a single, larger black hole. If early galaxies underwent frequent mergers, their black holes could have grown rapidly through repeated coalescence. However, mergers alone cannot fully explain the observed masses. Even with optimistic merger rates, simulations struggle to produce billion solar mass black holes within the first 500 million years. James Webb's detection of supermassive black holes at high redshifts has another implication. It suggests that the relationship between black holes and their host galaxies was different in the early universe. In the local universe, there's a tight correlation between the mass of a galaxy's central black hole and the mass of its stellar bulge. This relationship suggests that black holes and galaxies co-evolve, with feedback from the black hole regulating star formation in the galaxy. But in early galaxies, black holes appear to be disproportionately massive compared to their host galaxies. Some high redshift galaxies have black holes that are 10 to 100 times more massive, relative to their stellar mass, than black holes in present-day galaxies. This mismatch implies that black holes formed or grew faster than their host galaxies in the early universe. One explanation is that black holes formed first, then helped trigger the formation of their host galaxies by heating and ionizing the surrounding gas, which could collapse and form stars. Another possibility is that early black holes accreted gas so efficiently that they outpaced their host galaxies' star formation. Over cosmic time, as galaxies continued to grow through mergers and accretion, the black hole to galaxy mass ratio gradually decreased, approaching the values we see today. The role of dark matter in rapid galaxy formation. Dark matter is the invisible scaffold upon which all galaxies are built. Though it emits no light and interacts only through gravity, it comprises roughly 85% of the total matter in the universe. Without dark matter, galaxies as we know them could not exist. Its gravitational pull is what gathers ordinary matter, hydrogen and helium gas into dense clumps, initiating the process of star and galaxy formation. Understanding how dark matter behaved in the early universe is essential to explaining why James Webb is finding galaxies that formed far earlier and more rapidly than standard models predict. The timeline for this hierarchical assembly is well defined in simulations. According to Lambda CDM, the first dark matter halos capable of hosting galaxies should have formed around 100 to 200 million years after the Big Bang. These halos would have been small, with masses equivalent to a few million to a few 100 million times the mass of the Sunday gas. Falling into these halos would cool and condense, forming the first stars. Over hundreds of millions of years, these small halos would merge, building larger and larger structures, eventually giving rise to the massive galaxies we see in the universe today. But James Webb's observations challenge this picture. Galaxies like JADESGSZ130, observed at a redshift of 13.2, are far more massive than Lambda CDM predicts for their age. To contain a billion solar masses of stars, these galaxies must reside in dark matter halos, with total masses of at least 100 billion to a trillion solar masses. Yet standard simulations suggest that halos of this size shouldn't have assembled until 500 million to 1 billion years after the Big Bang, significantly later than the observed galaxies. One possible explanation is that dark matter halos in the early universe grew faster than current models predict. If the initial density fluctuations from inflation were slightly stronger in certain regions, those regions would have collapsed more quickly, forming massive halos earlier. Alternatively, if dark matter particles have properties slightly different from those assumed in Lambda CDM, it could alter the timeline of halo formation. For example, if dark matter has slight self-interactions, meaning dark matter particles occasionally collide with one another, it could change how halos collapse and merge, potentially accelerating the growth of large structures. Another possibility involves the efficiency of gas cooling within dark matter halos. In the standard picture, gas falling into a dark matter halo heats up due to gravitational compression. Before stars can form, this gas must cool and condense. Cooling typically occurs through radiative processes. Atoms and molecules emit photons, carrying away energy. In the early universe, the gas was mostly hydrogen and helium, which are inefficient coolants. Molecular hydrogen can cool gas to a few hundred degrees Kelvin, allowing it to collapse and form stars, but the process is slow. If cooling was somehow more efficient in early halos, perhaps due to unexpected chemical pathways, or the influence of nearby radiation gas could have collapsed and formed stars more rapidly, leading to the early appearance of massive galaxies. Some researchers have proposed that the first galaxies might have formed in regions of the universe with unusually high densities, so-called overdense regions. In these areas, dark matter halos would have been closer together, increasing the likelihood of mergers and interactions. Frequent mergers could have rapidly built up massive halos, and the enhanced gravitational potential would have pulled in gas more efficiently, accelerating star formation. If JADESGSZ 130 and similar galaxies formed in such overdense regions, it could explain their early appearance without requiring fundamental changes to the Lambda CDM model. However, this explanation has its own challenges. Overdense regions in the early universe are rare, and finding multiple massive galaxies in such regions requires either extraordinary luck or a much higher frequency of overdensities than simulations predict. Moreover, if early galaxies formed primarily in overdense regions, we would expect to see clustering groups of galaxies close together in space. While some clustering has been observed in Webb's high redshift samples, it's not yet clear whether the level of clustering matches what would be expected from overdense formation scenarios. Another line of inquiry involves the nature of dark matter itself. Lambda CDM assumes that dark matter is a single species of particle, typically a hypothetical weakly interacting massive particle, or WIMP. But what if dark matter is more complex? Some physicists have proposed that dark matter could consist of multiple particle types, each with different properties. If a fraction of dark matter is warm rather than cold, meaning its particles move faster, it could smooth out small-scale density fluctuations while allowing larger structures to collapse more easily. This could lead to the early formation of massive halos while suppressing the formation of smaller ones. Observations of the abundance and distribution of small satellite galaxies around the Milky Way and other galaxies could test this hypothesis, as warm dark matter would produce fewer small satellites than cold dark matter. A more exotic possibility is that dark matter interacts with ordinary matter through forces other than gravity. If dark matter particles can occasionally collide with protons or electrons, they could transfer energy to the gas within halos, affecting how it cools and collapses. Such interactions would need to be extremely weak otherwise. We would have detected them in laboratory experiments, but even faint interactions could have significant effects over cosmic timescales. Some models suggest that dark matter could have slight interactions with photons, allowing it to absorb or emit light under certain conditions. If true, this could alter the thermal history of the early universe, potentially affecting the timeline of galaxy formation. The impossibility of pre-Big Bang galaxies. The title of this exploration hinges on a provocative idea: a galaxy older than the Big Bang. On its face, this seems impossible, a logical contradiction. The Big Bang, by definition, marks the beginning of time, space, and matter. How can anything exist before the beginning? Yet the discovery of galaxies like JADESGSZ 130 whose stellar populations appear to require more time to form than the universe's age allows, forces us to confront this paradox. Either our measurements are wrong, our models are incomplete, or something far stranger is happening. The concept of older than the Big Bang emerges from a mismatch between observed galaxy properties and the timeline provided by Lambda CDM cosmology. JADESGSZ 130 at a redshift of 13.2 is observed as it existed 325 million years after the Big Bang. Yet spectroscopic analysis reveals that it contains stars with high metallicities, indicating multiple generations of stellar evolution. If each stellar generation takes 50 to 100 million years to complete its life cycle, then 3 generations would require 150 to 300 million years. Adding the time needed for the first dark matter halos to collapse and the first stars to ignite at least 100 million years brings the total timeline to 250 to 400 million years. But if the galaxy is observed at 325 million years, the math doesn't work. The galaxy's stellar populations appear to require more time than has elapsed since the Big Bang. This is not a claim that the galaxy literally formed before the Big Bang. Rather, it's a signal that something in our understanding is broken. The most straightforward interpretation is that our models of stellar evolution, star formation efficiency, or chemical enrichment in the early universe are incorrect. Perhaps stars in the first galaxies evolved faster, or perhaps star formation proceeded at rates far higher than current simulations predict. If the initial mass function was heavily skewed toward massive stars, those stars would have lived and died quickly, compressing multiple generations into a shorter timescale. Another possibility is that our measurements of the galaxy's age are wrong. Redshift to age conversions depend on the Hubble constant and assumptions about the universe's composition and expansion history. If the true Hubble constant is higher than the CMB-derived value as local measurements suggest the universe is younger, which makes the problem worse. But if the Hubble constant has varied over time, or if dark energy behaved differently in the early universe, the relationship between redshift and cosmic time could be more complicated than we assume. In that case, a galaxy at redshift 13.2 might not correspond to 325 million years after the Big Bang, but to some other longer timescale that provides more room for stellar evolution. A more radical interpretation involves reconsidering the Big Bang itself. In standard cosmology, the Big Bang is a singularity, a point of infinite density and temperature where the known laws of physics break down. General relativity, which describes gravity and the large-scale structure of the universe, predicts that time itself begins at this singularity. But general relativity is not the final word. It doesn't account for quantum mechanics, the theory governing the behavior of particles at the smallest scales. A complete theory of quantum gravity, something physicists have sought for decades, might reveal that the Big Bang singularity is not truly a beginning but a transition from some prior state. Several speculative models explore this possibility. In loop quantum cosmology, a framework that attempts to merge quantum mechanics with general relativity, the Big Bang is replaced by a big bounce. In this scenario, the universe previously existed in a contracting phase. As it shrank, quantum effects prevented it from collapsing into a singularity. Instead, the universe bounced, transitioning from contraction to expansion. If this bounce occurred, then the Big Bang as we know it is merely the most recent expansion phase, and the universe could have existed in some form before it. Density fluctuations or even protostructures from the previous phase could have carried over, potentially explaining why galaxies appear so mature so early. Cyclic cosmology offers yet another perspective. In these models, the universe undergoes repeated cycles of expansion and contraction, each cycle lasting trillions of years. At the end of each cycle, the universe contracts to a hot, dense state, then bounces and begins expanding again. The Big Bang is simply the most recent bounce. If structure from previous cycles somehow survived the bounce, perhaps encoded in the distribution of dark matter or in primordial density fluctuations, it could provide a head start for galaxy formation in the current cycle, explaining the early appearance of massive galaxies. All of these ideas remain highly speculative. None have been confirmed by observation, and most require extensions to known physics that have not been experimentally verified. But the fact that serious physicists are considering them reflects the depth of the crisis James Webb has created. When observations force you to question the most basic assumptions about the universe's history, even the most unconventional ideas deserve consideration. There is, of course, a simpler explanation. We don't yet fully understand how galaxies form. Lambda CDM is a framework, not a complete description of every physical process in the universe. It successfully predicts the large-scale structure of the cosmos, the properties of the cosmic microwave background, and the distribution of galaxies across billions of light-years. But it relies on assumptions about star formation, gas cooling, black hole growth, and numerous other astrophysical processes that are not fully understood. If any of these processes operated differently in the early universe faster, more efficiently, or through mechanisms we haven't yet considered, it could reconcile Webb's observations with the standard cosmological timeline, alternative cosmological models under scrutiny. The crisis precipitated by James Webb's discoveries has sent cosmologists scrambling to revisit alternative models of the universe, frameworks that were once considered fringe or speculative, but now demand renewed attention. If Lambda CDM cannot explain the existence of massive mature galaxies within the first few 100 million years after the Big Bang, then perhaps the assumptions underlying Lambda CDM are incorrect. This has led to a resurgence of interest in modified cosmologies, some of which propose fundamentally different pictures of how the universe began, evolved, and formed structure. One of the most discussed alternatives involves modifying the behavior of dark energy. In Lambda CDM, dark energy is represented by the cosmological constant, a fixed energy density that remains constant throughout cosmic history. But what if dark energy is not constant? Models of quintessence propose that dark energy is a dynamic field whose density changes over time. If dark energy was weaker in the early universe, gravity would have dominated more strongly, allowing structures to collapse and form faster. As the universe aged, dark energy would have grown stronger, eventually driving the accelerated expansion we observe today. This scenario could provide more time for early galaxies to form without altering the present-day expansion rate. Quintessence models come in many varieties, depending on the properties of the hypothetical field. Tracker quintessence models allow the dark energy density to evolve in a way that tracks the density of matter or radiation, keeping the universe's expansion rate close to the critical value. Phantom dark energy models, by contrast, suggest that dark energy density increases over time, potentially leading to a big rip in the distant future, where the universe's expansion accelerates so violently that it tears apart galaxies, stars, and eventually atoms. While these models can be tuned to match current observations, they introduce new parameters and require new physics beyond the cosmological constant, making them more complex and less predictive. Another alternative involves modifying gravity itself. General relativity has been tested extensively in the solar system and in strong field environments like neutron stars and black holes, but its predictions on cosmological scales spanning billions of light years and billions of years are harder to verify. Some physicists have proposed modifications to general relativity that change how gravity behaves at very large distances or at very early times. These modified gravity theories, such as MOND, modified Newtonian dynamics, or FR gravity, alter the gravitational force law in ways that could affect the formation of structure in the universe. In standard general relativity, gravity is described by Einstein's field equations, which relate the curvature of spacetime to the distribution of matter and energy. Modified gravity theories tweak these equations, introducing additional terms that become important under certain conditions. For example, free gravity replaces the standard Einstein-Hilbert action, the mathematical expression from which Einstein's equations are derived, with a more general function of the Ricci scalar, a measure of spacetime curvature. Depending on the form of this function, FR gravity can produce accelerated expansion without requiring dark energy, or it can alter the growth rate of density perturbations, potentially speeding up the formation of galaxies in the early universe. However, modified gravity theories face significant challenges. Most are tightly constrained by observations of the cosmic microwave background, the large-scale distribution of galaxies, and the bending of light around massive objects' gravitational lensing. These observations are remarkably consistent with standard general relativity, leaving little room for deviations. Moreover, Modified gravity theories often introduce instabilities or unphysical behavior in certain regimes, making them difficult to construct in a self-consistent way. A more exotic class of models involves extra dimensions. String theory, a candidate for a unified theory of all forces and particles, predicts that the universe has more than the 4 dimensions, 3 spatial, 1 temporal, we experience. The extra dimensions are typically assumed to be compactified, curled up so small that they're undetectable at ordinary energies. But some models suggest that extra dimensions could have observable effects on cosmology. For example, in brane world scenarios, our universe is a 4-dimensional brane embedded in a higher dimensional space. Gravity can propagate through the extra dimensions, leading to modifications of gravity at very short or very long distances. Such modifications could affect the early universe's expansion rate or the growth of structure, potentially explaining the rapid formation of galaxies. Cyclic and bouncing cosmologies offer a different approach. Instead of starting with a singular Big Bang, these models propose that the universe undergoes repeated cycles of expansion and contraction. In the ekpyrotic model, for example, our universe is one of 2 branes moving through a higher dimensional space. Periodically, the branes collide, triggering a bang that appears to us as a Big Bang but is actually a transition between cycles. Structure from a previous cycle could survive the collision, seeding the formation of galaxies in the current cycle. This could explain why galaxies appear so mature so early. They're not forming from scratch but building on remnants from a previous era. Loop quantum cosmology, mentioned earlier, replaces the Big Bang singularity with a quantum bounce, where the universe transitions from a contracting phase to an expanding phase. Quantum effects prevent the density from becoming infinite, avoiding the singularity. In this framework, the universe could be much older than 13.8 billion years if we count the time before the bounce. Alternatively, even if the bounce occurred 13.8 billion years ago, the properties of the pre-bounce phase could have influenced the initial conditions of our universe, leading to faster or more efficient structure formation. All of these alternative models share a common feature. They require new physics beyond the standard model of particle physics or general relativity. In science, new physics is typically invoked only when existing theories fail to explain observations. For decades, Lambda CDM passed every test. The cosmic microwave background, the large-scale distribution of galaxies, the abundances of light elements produced in the first few minutes after the Big Bang, all matched Lambda CDM predictions with remarkable precision. But James Webb's discovery of early, massive galaxies represents a significant failure. Whether this failure can be resolved within Lambda CDM through better understanding of astrophysical processes, or whether it requires new cosmology, remains an open question. The nature of time and cosmic chronology. At the heart of the older than the Big Bang paradox lies a question that physics has grappled with for centuries. What is time? In everyday experience, time flows forward a river carrying us from past to future. Events happen in sequence, causes precede effects, and the universe has a clear chronological order. But in cosmology, time is not a simple, absolute quantity. It's woven into the fabric of space-time, shaped by gravity and the expansion of the universe. Understanding what it means for something to be old, in a cosmological sense, requires unpacking how time itself is defined and measured. In special relativity, Einstein showed that time is relative. 2 observers moving at different speeds will disagree about how much time has elapsed between events. A clock on a fast-moving spaceship ticks more slowly compared to a clock on Earth, a phenomenon known as time dilation. This effect is real and measurable. GPS satellites, for example, must account for relativistic time dilation to maintain accurate positioning. In special relativity, there is no universal now. Simultaneity depends on the observer's frame of reference. General relativity extends this relativity of time to include gravity. Near a massive object, space-time is curved and time flows more slowly. A clock near a black hole's event horizon ticks far slower than a clock far away in flat space. This gravitational time dilation has been confirmed by observations of light from white dwarfs and neutron stars, and it plays a crucial role in cosmology. When we talk about the age of the universe, we're referring to the time experienced by a hypothetical observer moving with the average expansion of the universe, an observer who sees the cosmic microwave background as uniform in all directions. This cosmic time is the time coordinate used in Lambda CDM cosmology. It starts at 0 at the Big Bang and progresses forward as the universe expands. When we say the universe is 13.8 billion years old, we mean that 13.8 billion years of cosmic time have elapsed since the Big Bang, as measured by a clock moving with the Hubble flow. But cosmic time is not the only way to measure time. In principle, one could define time differently using the temperature of the cosmic microwave background, the density of matter, or some other physical quantity that changes as the universe evolves. Different choices of time coordinate can lead to different descriptions of the same physical events. This raises a subtle question. When we observe a galaxy at redshift 13.2, what does its age actually mean? We calculate that the light from this galaxy was emitted 325 million years after the Big Bang, based on the redshift distance-time relation in Lambda CDM. But this calculation assumes a specific expansion history for the universe, one driven by matter, radiation, and a cosmological constant. If the universe's expansion history was different, if dark energy evolved, or if gravity behaved differently at early times, the relationship between redshift and cosmic time would change. A galaxy at redshift 13.2 might correspond to a different age than 325 million years. Moreover, time as experienced within the galaxy itself could differ from cosmic time. If the galaxy formed in a region of unusually high density, gravitational time dilation would cause time to flow more slowly there compared to the surrounding space. Over hundreds of millions of years, this effect could accumulate, meaning that more cosmic time elapsed than the galaxy experienced. However, for typical galaxies, this effect is tiny, on the order of fractions of a percent, and cannot resolve the timeline crisis. Another aspect of cosmic chronology involves the concept of conformal time, a time coordinate often used in cosmological calculations. Conformal time accounts for the expansion of the universe by measuring time not in years, but in terms of how far light could have travelled since the Big Bang. In conformal time, the Big Bang occurred at an infinite distance in the past, and the present moment is at a finite conformal time. This choice of time coordinate is mathematically convenient, but it highlights that time in cosmology is not a single, absolute entity. It's a coordinate system we impose on the evolving space-time of the universe. The possibility that the Big Bang is not the true beginning of time adds yet another layer. In quantum cosmology, where quantum mechanics is applied to the entire universe, the concept of a beginning becomes ambiguous. The Wheeler-DeWitt equation, a quantum equation for the universe's wave function, does not include a time variable in the usual sense. This has led some physicists to propose that time is an emergent phenomenon, something that arises from the universe's quantum state rather than being fundamental. In such a framework, the Big Bang might not be a singular event but a quantum transition, and the notion of before the Big Bang could have meaning in a quantum sense, even if not in a classical one. String theory and related frameworks introduce additional complications. If the universe has extra dimensions, time might not be a single, one-dimensional parameter but part of a more complex structure. In some brain world models, time as we perceive it is confined to our four-dimensional brain, but the higher dimensional bulk in which the brain is embedded could have its own time-like dimensions. Events in the bulk could influence our universe without leaving a clear temporal signature, potentially affecting the initial conditions of the Big Bang or the rate at which structure forms. These considerations are not merely philosophical. They have practical implications for interpreting James Webb's observations. 1. If the universe's early expansion history was even slightly different from Lambda CDM's predictions due to evolving dark energy, modified gravity, or quantum effects near the Big Bang, the ages we assign to high redshift galaxies could be systematically wrong. A galaxy that appears to require 400 million years of evolution might fit within 300 million years if the expansion rate was different during that period. Alternatively, if time itself behaved differently in the early universe, flowing faster or slower due to quantum gravitational effects, the chronology of galaxy formation could be compressed or stretched in ways not captured by classical general relativity, observational biases and selection effects. When James Webb detects a galaxy at redshift 13, it's identifying one of the brightest, most massive, or otherwise most detectable objects from that era. But the universe at 300 million years after the Big Bang was filled with countless other galaxies fainter, smaller, and harder to see. the galaxies Webb finds are not a random sample of the early universe. They're the tip of the iceberg, the rare giants that shine brightly enough to be detected across 13.5 billion light-years of space. Understanding this selection bias is crucial for interpreting what Webb's discoveries mean for cosmology as a whole. If the early universe contained large numbers of faint, low-mass galaxies below Webb's detection threshold, their contribution to the total stellar mass and star formation rate would be significant. In that case, the few massive galaxies Webb detects might be rare outliers rather than representative examples. Lambda CDM could still be correct, with most early galaxies being small and faint as predicted, and Webb is simply finding the exceptional cases. However, if massive galaxies are common enough that Webb routinely detects them, it suggests a fundamental problem with the model. Initial analyses of Webb's high redshift galaxy samples suggest that massive galaxies are more common than Lambda CDM predicts. Surveys like JADES, SEERS, Cosmic Evolution Early Release Science, and GLASS, Grism Lens Amplified Survey from Space, have found dozens of galaxy candidates at redshifts above 10, and many of these are surprisingly bright. Statistical studies comparing the observed number of high redshift galaxies to Lambda CDM predictions indicate an excess more galaxies than expected, especially at the high mass end. This discrepancy persists even after accounting for uncertainties in photometric redshifts and the selection effects inherent in any survey. One complication is the phenomenon of gravitational lensing. When light from a distant galaxy passes near a massive foreground object, such as a galaxy cluster, the gravity of the foreground object bends the light, magnifying the background galaxy and making it appear brighter. Webb has used gravitational lensing strategically, observing behind massive clusters to detect galaxies that would otherwise be too faint to see. Lensing can boost a galaxy's apparent brightness by factors of 10, 100, or even more, allowing Webb to probe deeper into the early universe. However, lensing introduces its own selection biases. Lensed galaxies are not randomly distributed across the sky. They appear preferentially in regions where massive foreground clusters exist. Moreover, the degree of magnification varies across the lens, meaning that different parts of a lensed galaxy can be magnified by different amounts. This can distort the galaxy's apparent shape and brightness, complicating the interpretation of its physical properties. Astronomers must carefully model the lensing effect to infer the galaxy's true luminosity and size, and uncertainties in these models can lead to systematic errors. Another bias involves dust extinction. Dust grains in galaxies absorb and scatter light, particularly at shorter wavelengths like ultraviolet and visible light. Infrared light is less affected, which is one reason Webb's infrared instruments are so powerful. But even infrared light is not immune to dust. If early galaxies contain more dust than expected, perhaps due to rapid supernova enrichment, their true luminosity could be higher than what Webb observes, hidden behind a dusty veil. Conversely, if early galaxies have less dust, as many models predict, the observed luminosity is a more accurate reflection of their stellar mass and star formation rate. Estimating the dust content of high redshift galaxies is challenging. It requires observations at multiple wavelengths, particularly in the far infrared and submillimeter, where dust emission peaks. The Atacama Large Millimeter Submillimeter Array, ALMA, can detect this emission, and joint observations with Webb and ALMA are beginning to constrain the dust properties of early galaxies. So far, results are mixed. Some high redshift galaxies show little dust, consistent with models, while others appear surprisingly dusty, suggesting rapid chemical enrichment. Selection effects also arise from the cosmic variance, the statistical fluctuation in the number of galaxies in any given region of sky. Because galaxies are not uniformly distributed but cluster together, small survey areas can over or under-represent the true population. A survey that happens to observe an overdense region might detect more galaxies than average, creating the illusion of a higher-than-predicted abundance. Conversely, a survey targeting an underdense region might miss galaxies and underestimate their numbers. Cosmic variance is particularly problematic for high redshift surveys, where the observable volume is relatively small. Webb's early surveys covered only a few square arc-minutes of sky, a tiny fraction of the celestial sphere, meaning the detected galaxies might not be representative of the entire universe. To mitigate cosmic variance, astronomers are expanding Webb's surveys to cover larger areas of sky. Programs like Cosmos, Webb, and Primer aim to observe tens to hundreds of square arc minutes, increasing the statistical robustness of galaxy counts and reducing the impact of local overdensities. As these surveys progress, clearer patterns will emerge, helping to determine whether the abundance of massive early galaxies is truly anomalous or an artifact of small sample sizes. Another subtle bias involves spectroscopic confirmation. Many of Webb's high redshift galaxy candidates are initially identified through photometry measuring their brightness in different filters. By comparing these measurements to templates of galaxy spectra, astronomers estimate the galaxy's redshift. But photometric redshifts are uncertain, with errors that can place a galaxy at the wrong redshift by significant amounts. To confirm a galaxy's redshift, spectroscopy is required, which measures the precise wavelengths of spectral lines in the galaxy's light. However, spectroscopy is time-consuming, and only a fraction of photometric candidates have been spectroscopically confirmed. This introduces a potential bias. If only the brightest or most interesting candidates are selected for spectroscopic follow-up, the confirmed sample may not be representative. Faint or unremarkable galaxies might be left unconfirmed, even if they are genuinely at high redshift. This could lead to an overestimation of the typical brightness or mass of early galaxies. Alternatively, some photometric candidates might be interlopers, lower redshift galaxies whose colors mimic those of high redshift galaxies, leading to false identifications. Spectroscopy weeds out these interlopers, but if the false positive rate is high, the true abundance of early galaxies might be lower than initial photometric surveys suggest. The future of cosmology in the Webb era. The James Webb Space Telescope has only begun its mission. The observations that have already shaken cosmology represent a fraction of what the telescope will accomplish over its expected decade-long lifetime. As Webb continues to stare deeper into space and time, refining measurements, discovering new galaxies, and probing the physical conditions of the early universe, the field of cosmology will undergo a transformation. The questions raised by early galaxies like JADES GSZ 130 are just the beginning. The answers and the new questions they generate will shape our understanding of the universe for decades to come. One of Webb's primary goals is to map the timeline of reionization with unprecedented precision. Reionization marks the transition from the cosmic dark ages, when the universe was filled with neutral hydrogen, to the ionized state we observe today. This transition was driven by the first stars and galaxies, whose ultraviolet radiation ionized the surrounding gas. Lambda CDM predicts that reionization began around 400 to 500 million years after the Big Bang and completed by about 1 billion years. But the exact timeline when it started, how fast it progressed, and which types of galaxies contributed most remains uncertain. Webb's infrared spectrograph, NIRSpec, can detect the signatures of neutral hydrogen by observing the Lyman alpha line, a spectral feature emitted by hydrogen atoms. In a fully neutral universe, Lyman alpha photons are absorbed by the surrounding gas, preventing them from reaching us. As reionization progresses and bubbles of ionized gas grow, Lyman alpha photons can escape from galaxies, becoming visible. By measuring the Lyman alpha visibility in galaxies at different redshifts, Webb can trace how the ionized fraction of the universe evolved over time. Early results suggest that reionization might have occurred earlier and faster than models predict, consistent with the abundance of bright galaxies Webb observes. Another key question Webb will address is the nature of the first stars, population 3 stars. These hypothetical objects, composed entirely of hydrogen and helium, have never been directly observed. They are expected to be extremely massive and short-lived, with no survivors remaining in the present-day universe. But their influence persists. The heavy elements they produced seeded the first galaxies, and their ultraviolet and supernova feedback shaped the early intergalactic medium. Webb might be able to detect the signatures of population 3 stars indirectly, either by observing galaxies with extremely low metallicities or by detecting the unique spectral features produced by their deaths. Webb will also continue to study supermassive black holes in the early universe. Understanding how these black holes formed and grew so rapidly is one of the most pressing problems in astrophysics. Webb's infrared sensitivity allows it to detect the faint light from active galactic nuclei galaxies powered by accreting black holes at redshifts beyond 10. By measuring the masses, accretion rates, and environments of these black holes, astronomers can test models of black hole formation and growth. One particularly exciting possibility is the discovery of intermediate mass black holes, objects with masses between 100 and 100,000 solar masses, which could serve as the seeds of supermassive black holes. The telescope's imaging capabilities will also allow detailed studies of galaxy morphology in the early universe. Are early galaxies irregular and clumpy, as simulations predict, or do they show signs of ordered structure like spiral arms or bars? Webb's near-infrared camera, NIRCam, can resolve features as small as a few hundred light-years in distant galaxies, revealing their internal structure. Early images suggest that some high-redshift galaxies are surprisingly compact, with much of their stellar mass concentrated in small, dense cores. Understanding why these galaxies are so compact and how they eventually grow into the larger, more diffuse galaxies we see today will require detailed modelling and comparison with simulations. Beyond individual galaxies, Webb will study the large-scale structure of the universe in its infancy. By mapping the distribution of galaxies across the sky at different redshifts, astronomers can trace how the cosmic web evolved. Are high redshift galaxies clustered together, or are they more evenly distributed? Do they lie along filaments and walls, as predicted by Lambda CDM, or is the structure different in the early universe? These questions bear directly on our understanding of dark matter and the growth of structure under gravity. Webb's data will also provide critical input for next-generation simulations. Cosmological simulations such as Illustris, EAGL, and the Millennium simulation model the formation and evolution of galaxies from the Big Bang to the present. These simulations require immense computational power and incorporate complex physics, gravity, gas dynamics, star formation, supernova feedback, black hole growth, and more. By comparing simulation outputs to Webb's observations, astronomers can test and refine the physical models encoded in the simulations. If simulations can reproduce the abundance, masses, and properties of early galaxies, it suggests the underlying physics is correct. If not, new physics must be added. Perhaps most importantly, Webb's discoveries will inform the design of future missions. NASA and its international partners are already planning observatories that will push beyond Webb's capabilities. The Habitable Worlds Observatory, for example, will focus on detecting and characterizing Earth-like planets around nearby stars, but its advanced instrumentation could also probe the early universe. Concepts for a Webb successor, a telescope with an even larger mirror and more sensitive instruments, are being discussed. Such a mission could detect galaxies at redshifts of 15, 20 or even higher, peering closer to the Big Bang than ever before. It could also study the first galaxies in exquisite detail, measuring their chemical compositions, star formation histories, and dynamics with precision far exceeding Webb's. The theoretical response to Webb's discoveries is equally important. Cosmologists are already revising models, running new simulations, and exploring alternative theories. The next few years will see intense scrutiny of Lambda CDM, with researchers testing every assumption and parameter. If the model survives, if modifications to star formation efficiency, black hole growth, or gas cooling can explain Webb's observations, it will emerge stronger and more refined. If it fails, cosmology will enter a period of upheaval, with competing models vying to replace the standard framework. The cosmic microwave background and early universe constraints. The cosmic microwave background radiation, or CMB, is the oldest light in the universe, a faint glow of photons released roughly 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. This relic radiation, discovered accidentally in 1965 by Arno Penzias and Robert Wilson, has become one of cosmology's most powerful tools. Satellites like COBE, WMAP, and Planck have mapped the CMB's temperature fluctuations across the entire sky with exquisite precision, revealing tiny variations about 1 part in 100,000 that represent the seeds of all cosmic structure. These fluctuations encode information about the universe's composition, geometry, and initial conditions. And crucially, they place strict constraints on when and how the first galaxies could have formed. The CMB's temperature pattern is remarkably uniform, confirming that the early universe was nearly homogeneous. The tiny fluctuations that do exist correspond to regions that were slightly denser or less dense than average. Over time, gravity amplified these density variations. Denser regions attracted more matter and grew into the dark matter halos that eventually hosted galaxies, while less dense regions became cosmic voids. The statistical properties of these fluctuations, their amplitude, their distribution across different angular scales, match the predictions of Lambda CDM with extraordinary precision. This agreement is one of the model's greatest triumphs, and one reason why cosmologists have been reluctant to abandon it despite Webb's puzzling observations. The CMB data provide a snapshot of the universe at 380,000 years old, but they also constrain what happened later. The polarization of CMB photons, the orientation of their electromagnetic waves, carries information about reionization. When the first stars and galaxies ionized the intergalactic medium hundreds of millions of years later, they scattered CMB photons, imprinting a distinctive polarization signature. Planck's satellite measurements of this reionization signal suggest that reionization occurred around 400 to 600 million years after the Big Bang, with significant uncertainty. This timeline is broadly consistent with pre-Webb observations of distant quasars and galaxies, but James Webb's discovery of abundant bright galaxies at redshifts of 10 to 14 implies that reionization might have begun earlier and proceeded faster than the CMB polarization data suggest. This creates tension. If numerous massive galaxies existed by 300 to 400 million years after the Big Bang, they would have emitted vast amounts of ultraviolet radiation, ionizing their surroundings and contributing to the CMB's reionization signal. The more abundant and luminous these early galaxies, the stronger the expected signal. Yet Planck's measurements indicate a relatively modest optical depth to reionization, a quantity that measures how much the CMB photons were scattered by free electrons during reionization. A low optical depth suggests that reionization occurred relatively late and that the ionizing photon budget was limited. Webb's galaxies, if they're as common as early observations suggest, would produce more ionizing photons, increasing the optical depth beyond what Planck measures. Several explanations have been proposed to resolve this discrepancy. One possibility is that early galaxies were less efficient at ionizing the intergalactic medium than their brightness suggests. Ultraviolet photons produced by young stars can be absorbed by dust within the galaxy, or by neutral hydrogen in the galaxy's immediate surroundings, preventing them from escaping into intergalactic space. If the escape fraction of ionizing photons, the percentage that actually leave the galaxy, was lower than assumed, early galaxies could be bright in the infrared, which Webb detects without contributing significantly to reionization. Alternatively, if early galaxies were heavily obscured by dust, much of their ultraviolet light would be absorbed and re-emitted in the infrared, making them appear bright to Webb but reducing their ionizing impact. Another explanation involves the clumpiness of reionization. The process didn't occur uniformly across the universe but proceeded in a patchy manner, with ionized bubbles forming around clusters of galaxies and gradually merging. If reionization was highly inhomogeneous, with some regions ionizing early while others remained neutral for longer, the integrated CMB signal could differ from what simple models predict. Webb's observations might be preferentially detecting galaxies in overdense regions that ionized early, while missing galaxies in average or underdense regions. This selection effect could create the impression that bright galaxies were more common than they actually were across the universe as a whole. The initial density fluctuations imprinted during inflation also constrain galaxy formation. These fluctuations, characterized by the primordial power spectrum, determine the amplitude of density variations at different scales. Lambda CDM assumes a nearly scale-invariant power spectrum, meaning fluctuations have similar amplitudes at all scales, with only a slight preference for larger scales. This assumption is based on the simplest models of inflation and is strongly supported by CMB data. But if the primordial power spectrum were tilted more strongly with greater amplitude on small scales, it would enhance the formation of small dark matter halos in the early universe, potentially accelerating galaxy formation. Some physicists have explored whether modifications to inflation could produce such a spectrum while remaining consistent with CMB observations, but the parameter space is tightly constrained. Recent analyses combining CMB data with Webb's galaxy observations are beginning to reveal where the tensions lie. Some studies suggest that if the abundance of bright galaxies at redshifts above 10 is confirmed, it implies either a higher star formation efficiency than assumed, a top-heavy initial mass function producing more luminous stars per unit mass, or a systematic error in converting observed luminosity to stellar mass. Each of these possibilities has implications for the physics of the early universe that go beyond simple adjustments to Lambda CDM parameters. The interplay between CMB constraints and direct galaxy observations will intensify as Webb's datasets grow. Future CMB missions, such as CMB S4 and Lightbird, will measure the polarization signal with even greater precision, potentially detecting the faint signature of primordial gravitational waves from inflation and refining the reionization optical depth. These measurements will either tighten the constraints on early galaxy formation, making the tension with Webb's observations more acute, or reveal subtle deviations from Lambda CDM that point toward new physics. Either outcome will advance our understanding, but the former would deepen the crisis, while the latter could provide the first hints of a resolution. Galaxy mergers and hierarchical assembly in question. One of the foundational principles of Lambda CDM cosmology is hierarchical structure formation, the idea that large structures in the universe grow from small ones through a bottom-up process. Dark matter halos begin as tiny overdensities in the primordial universe, gradually growing through mergers and accretion. Galaxies form within these halos and likewise grow by merging with one another, building ever larger systems over cosmic time. This hierarchical assembly naturally predicts that the first galaxies should be small and that massive galaxies should only appear later, after many generations of mergers. Yet James Webb's observations suggest a different story. Massive galaxies appearing remarkably early, possibly before the standard hierarchical process had time to operate. In the Lambda CDM framework, galaxy mergers are not rare events but common occurrences throughout cosmic history. When two dark matter halos approach each other, gravitational attraction pulls them together. If they collide, dynamical friction, a process where gravitational interactions between particles drain orbital energy, causes the halos to spiral inward and eventually merge. The galaxies embedded in these halos merge as well, combining their stellar populations and often triggering intense bursts of star formation as gas clouds collide and compress. Over billions of years, repeated mergers build the massive elliptical and spiral galaxies we see in the local universe. Simulations of hierarchical assembly, such as the Millennium Simulation and Illustris, reproduce the observed properties of present-day galaxies remarkably well. They predict the correct distribution of galaxy masses, the clustering of galaxies into groups and clusters, and the morphological mix of spirals, ellipticals, and irregular galaxies. The success of these simulations has reinforced confidence in the hierarchical paradigm. But when the same simulations are run backward in time, predicting what the universe should look like at redshifts of 10 or higher, they consistently underpredict the number and masses of the galaxies James Webb observes. The problem is timing. According to simulations, the first dark matter halos massive enough to host bright galaxies, halos with masses of 100 billion to 1 trillion solar masses, should not have assembled until 500 million to 1 billion years after the Big Bang. Before that time, only smaller halos, containing a few billion to tens of billions of solar masses, should exist. These smaller halos can host dwarf galaxies with stellar masses of a few million to a few hundred million solar masses, but not the billion solar mass galaxies Webb detects at redshifts of 13. To reach such high masses so early, either the halos assembled faster than simulations predict, or the efficiency of converting gas into stars within those halos was far higher than assumed. One possible resolution involves extremely efficient early mergers. If small halos in overdense regions merge rapidly and repeatedly, they could build massive halos in less time than average. This scenario requires an unusually high merger rate in the early universe, driven perhaps by the higher density of matter at early times or by the specific properties of the initial density fluctuations. Some recent simulations exploring variations in the primordial power spectrum, the distribution of density fluctuations at different scales, suggest that slight enhancements in small-scale power could accelerate halo assembly, though these models are constrained by CMB observations. Another factor is the role of gas accretion. Galaxies don't grow only through mergers, they also accrete gas from the surrounding intergalactic medium. In the early universe, gas densities were higher, and the temperature of the intergalactic medium was lower, making it easier for gas to cool and fall into dark matter halos. Cold gas streams, flowing along cosmic filaments, could have fed galaxies at high rates, sustaining vigorous star formation. Some simulations suggest that in the first billion years, gas accretion might have been the dominant mode of galaxy growth, with mergers playing a secondary role. If early galaxies accreted gas extremely efficiently, they could have built up large stellar masses without requiring unusually massive dark matter halos. Some researchers have proposed that the first galaxies might have experienced rapid bursts of star formation triggered by mergers, followed by long quiescent periods. In this scenario, a galaxy like JAD ESGSZ 130 could have formed most of its stars in a brief, intense starburst lasting only a few tens of millions of years, then remained relatively inactive afterward. Such bursts could be triggered by major mergers, where two comparably sized galaxies collide, compressing their gas and igniting widespread star formation. If we happen to observe the galaxy shortly after a burst, it would appear bright and massive, even if its average star formation rate over cosmic time was lower. However, spectroscopic observations of high redshift galaxies show evidence of ongoing star formation, not just post-starburst populations, suggesting that star formation was sustained rather than episodic. The morphology of early galaxies provides additional clues about their assembly history. If galaxies formed primarily through mergers, they should appear irregular and disturbed, with tidal tails, asymmetries, and clumpy structures. If they grew primarily through smooth gas accretion, they might show more regular, disk-like morphologies. Webb's high-resolution imaging reveals that many high-redshift galaxies are compact and highly concentrated, with most of their light coming from small central regions. Some show multiple bright clumps, possibly indicating ongoing mergers or regions of intense star formation. But the overall impression is one of surprising order. These galaxies don't look as chaotic as simulations of early mergers would predict. One intriguing possibility is that the hierarchical assembly process operates differently in the early universe. Standard simulations assume that the physics of galaxy formation, star formation, supernova feedback, black hole growth is the same at all times. But what if the conditions in the first few 100 million years after the Big Bang were fundamentally different? Higher gas densities, stronger radiation backgrounds, or different initial mass functions could all alter the efficiency of star formation and the dynamics of mergers. If early galaxies formed stars more efficiently per unit of gas mass, they could achieve high stellar masses even in relatively small dark matter halos, reducing the need for rapid halo assembly. The mystery of massive galaxies and star formation efficiency. Star formation is the process by which diffuse clouds of gas collapse under gravity, fragment into dense cores, and ignite nuclear fusion, giving birth to stars. In the present-day universe, star formation is relatively inefficient. For every 100 solar masses of gas in a molecular cloud, only about 1 to 10 solar masses actually become stars. The rest is dispersed by stellar winds, radiation pressure, and supernova explosions. This low efficiency is well documented in nearby star-forming regions like the Orion Nebula and is incorporated into models of galaxy evolution. But if star formation in the early universe was far more efficient, converting a much higher fraction of gas into stars, it could explain how massive galaxies assembled so quickly. The efficiency of star formation depends on several factors: the density and temperature of the gas, the strength of turbulence and magnetic fields, and the amount of feedback from previously formed stars. In the dense, metal-poor environment of the early universe, conditions might have favoured more efficient star formation. Gas clouds were more massive and more tightly bound by gravity, making them harder to disrupt. The absence of heavy elements meant that stellar winds and supernova ejecta contained less metal-enriched material, reducing the effectiveness of feedback in halting star formation. If these factors combine to increase star formation efficiency from the typical 1 to 10% up to 20, 30, or even 50%, galaxies could build stellar masses much faster. Observational evidence for high star formation efficiency comes from measurements of specific star formation rates, the rate of star formation per unit of existing stellar mass. In present-day galaxies, specific star formation rates are typically around 0.01 to 0.1 per billion years, meaning it takes billions of years to double a galaxy's stellar mass. But in some high redshift galaxies observed by Webb, specific star formation rates appear to be 1 to 10 per billion years, 10 to 100 times higher. If sustained, such rates would allow a galaxy to build a billion solar masses of stars in just 100 to 200 million years, fitting comfortably within the timeline between the end of the cosmic dark ages and the observed redshift of 13. However, sustaining such high star formation rates requires a continuous supply of gas. Galaxies consume gas as they form stars, and unless that gas is replenished through accretion from the intergalactic medium or through mergers, star formation will halt. In the early universe, gas accretion rates were likely higher due to the greater density of matter and the stronger gravitational pull of dark matter halos. Cold gas streams, flowing along cosmic Webb filaments, could have funneled enormous quantities of gas into galaxies, sustaining prolonged episodes of star formation. Some simulations suggest that early galaxies could have accreted gas at rates of 10 to 100 solar masses per year, more than enough to fuel the observed star formation. The initial mass function, the distribution of stellar masses produced in each episode of star formation, also plays a critical role. In the local universe, the initial mass function follows a characteristic pattern known as the Salpeter, or Krupa IMF, which produces relatively few massive stars and many low-mass stars. Massive stars are bright but short-lived, while low-mass stars are faint but long-lived. If the initial mass function in the early universe was top-heavy, producing a higher proportion of massive stars, each generation of star formation would be brighter and would produce heavy elements faster, accelerating both the galaxy's luminosity and its chemical enrichment. Evidence for a top-heavy IMF in early galaxies is mixed. Some spectroscopic observations of high redshift galaxies show strong emission lines from massive stars, suggesting an overabundance relative to low-mass stars. Other observations show stellar populations consistent with a standard IMF. Resolving this question requires detailed modelling of stellar populations and careful comparison with observations across multiple wavelengths. If a top-heavy IMF is confirmed, it would have profound implications for converting observed luminosity into stellar mass. Current estimates assume a standard IMF, so a top-heavy IMF would imply lower stellar masses than currently inferred, partially alleviating the tension with Lambda CDM. Webb's spectroscopic capabilities are beginning to shed light on these questions. By measuring emission lines from ionized gas in high redshift galaxies, astronomers can infer the properties of the stellar populations heating that gas. Strong emission from hydrogen and helium indicates the presence of hot, massive stars. Emission from heavy elements like oxygen, nitrogen, and sulfur provides clues about the galaxy's chemical enrichment history. Absorption lines from cooler stars reveal the presence of older stellar populations. Combining these observations with stellar population synthesis models allows astronomers to reconstruct the star formation history of each galaxy, determining when stars formed, how rapidly, and under what conditions. Early results suggest a diverse picture. Some high redshift galaxies show signs of ongoing, vigorous star formation, with little evidence of older stars, consistent with galaxies forming their first generation of stars. Others contain mixed populations, with both young, massive stars and older, cooler stars, indicating that star formation has been sustained over tens to hundreds of millions of years. Still others show post-starburst signatures, where star formation has recently ceased, leaving behind a population of aging stars. This diversity suggests that the early universe was not uniform. Different galaxies formed under different conditions and followed different evolutionary paths. The spatial distribution of star formation within early galaxies adds another layer of complexity. In present-day galaxies, star formation often occurs in spiral arms or in nuclear rings around the galactic center. In early galaxies, Webb's imaging reveals compact, highly concentrated star formation, with much of the activity occurring in the central few hundred parsecs. This concentration could be driven by rapid gas inflows funneling material toward the galactic center, or by gravitational instabilities in gas-rich disks that fragment into dense star-forming clumps. Understanding the spatial distribution of star formation helps constrain the physical processes driving it, and provides insights into how early galaxies assembled their stellar mass. The search for population 3, stars and primordial signatures. Hidden somewhere in the early universe, perhaps within the very galaxies James Webb now observes, lies one of astronomy's holy grails, the first generation of stars. Called population 3 stars, these hypothetical objects are fundamentally different from every star visible in the night sky today. They formed from pristine gas, pure hydrogen, and helium forged in the Big Bang, untouched by any prior stellar generation. No oxygen fueled their fusion, no carbon seeded their cores, no iron reinforced their structure. They were cosmic pioneers, the first light-bringers in a universe emerging from darkness. Despite decades of theoretical work, no population 3 star has ever been directly observed. But James Webb, with its unprecedented infrared sensitivity, might finally change that. The physics of population 3 stars differs dramatically from modern stellar physics. In present-day star formation, heavy elements play a crucial role in cooling gas clouds. When carbon, oxygen, and other metals are present, they act as efficient radiators, absorbing thermal energy and emitting it as photons, allowing gas to cool from millions of degrees down to the hundreds or thousands of degrees needed for gravitational collapse. But in the primordial universe, with metallicity effectively zero, only atomic and molecular hydrogen could facilitate cooling. Molecular hydrogen is far less efficient than metals, meaning primordial gas clouds had to be more massive and hotter to collapse and form stars. Theoretical models predict that population 3 stars were giants, perhaps 100 to 300 times the mass of the Sun, though some models suggest a range spanning from 10 to 1,000 solar masses. These massive stars would have burned brilliantly but briefly, with lifetimes measured in mere millions of years. Their surface temperatures would have exceeded 100,000 Kelvin, making them intensely luminous in ultraviolet light. A single population 3 star could have outshone entire present-day dwarf galaxies, flooding its surroundings with ionizing radiation capable of clearing bubbles of neutral hydrogen hundreds of light-years across. When these stars exhausted their fuel, they would have died in spectacular hypernova explosions, seeding the universe with its first heavy elements and possibly collapsing into the first stellar mass black holes. The chemical signature of population 3 stars should be distinctive. Since they formed from pure hydrogen and helium, their atmospheres would contain no metals. However, detecting such a star directly is extraordinarily difficult. Population 3 stars lived fast and died young, meaning none should survive in the present-day universe. Any population 3 star that formed would have exploded as a supernova within a few million years, dispersing its material into space. The only way to observe one would be to catch it during its brief lifetime, which means looking back to the first few 100 million years after the Big Bang, precisely the epoch Webb is now exploring. One strategy for finding population 3 stars involves searching for their distinctive spectral signatures in high redshift galaxies. If a population 3 star is actively burning in an early galaxy, it should produce an unusual emission spectrum dominated by hydrogen and helium lines, with no trace of heavier elements. The star's extreme temperature would produce strong Lyman alpha emission and intense ionizing radiation. Webb's near-spec instrument can detect these features, but distinguishing a population 3 star from other sources, such as massive population 2 stars with very low but non-zero metallicity, requires exquisite spectral resolution and careful analysis. Another approach searches for the supernovae of population 3 stars, known as pair instability supernovae. These explosions occur when a very massive star's core becomes so hot that photons spontaneously convert into electron-positron pairs, reducing radiation pressure and causing the core to collapse catastrophically. The result is an explosion far more powerful than ordinary supernovae, releasing energies of 10 to 100 times greater and producing distinctive nucleosynthetic signatures. The supernova ejects enormous quantities of oxygen, magnesium, and silicon, but relatively little iron compared to normal supernovae. If Webb detects a transient event in a high redshift galaxy with this unusual chemical signature, it could be witnessing the death of a population 3 star. Recent theoretical work suggests that population 3 stars might have formed in multiple waves rather than a single generation. The first wave would have enriched small patches of the intergalactic medium, but vast regions would have remained pristine. In these metal-free pockets, subsequent generations of population 3 stars could have formed, extending the population 3 era over hundreds of millions of years. If this extended population 3 scenario is correct, Webb has a better chance of detecting these stars at redshifts between 10 and 15, where both the cosmic volume is larger and the observational sensitivity is higher. Gravitational lensing offers a powerful tool for detecting population 3 stars. Massive galaxy clusters can magnify the light from background objects by factors of 10, 100, or even 1000, effectively turning Webb into an even more powerful telescope. By observing lensed high-redshift galaxies, Webb can resolve structures as small as a few light-years, across small enough to detect individual bright stars or compact star clusters. Several programs are underway to exploit this technique, targeting the most strongly lensed regions behind clusters like Abell 2000, 744, and Max J 416. If population 3 stars exist in these lensed galaxies, their extreme brightness might make them stand out as point sources, distinguishable from the diffuse background light. The stakes are high. Detecting a population 3 star would confirm a fundamental prediction of cosmology and stellar evolution, providing direct evidence of the universe's transition from darkness to light. It would reveal the properties of the first stars, their masses, temperatures, and luminosities, and test theoretical models that have guided astrophysics for decades. More broadly, it would mark a milestone in humanity's understanding of cosmic origins, connecting the abstract physics of the Big Bang to the tangible reality of stars and galaxies. James Webb's infrared eye is our best hope for making this discovery. If population 3 stars are out there, Webb will find them.